Welcome to the series of lecture on finite element analysis. In this part, we are going to continue the transverse vibration of beam problems. In this part, we are going to see how to derive the natural frequencies of simply supported beam and fixed beam. In earlier part, we have discussed about what is vibration and how to define the vibration behavior of a beam or any structure. So vibrations are nothing but repeated motion. Any motion which repeats itself after equal interval of time, we call it as vibration. These vibrations are characterized by using the parameters like frequency, amplitude and mode shapes. So here we are going to evaluate the natural frequencies of simply supported beam and fixed beam. To determine the natural frequency of a beam, first we have to convert that beam into a mathematical model. The mathematical model of a beam problem which is subjected to transverse vibration is already we discussed. So we derived the governing differential equation of fourth order, and we are using always the frequency domain in beam problem because we have many advantages by using the frequency domain that we have discussed earlier. Then using this mathematical model, we derived the element characteristic equation for this transverse vibration of beam problem. So this is the element characteristic equation we derived. So the general format will be the stiffness matrix K minus omega square multiplied with the mass matrix M. So this is the 4 by 4 K matrix and this is the 4 by 4 mass matrix. Both are square and symmetrical matrix. So in the major diagonal we have the non-zero non-negative elements like this. So for beam we are assuming 2 degrees of freedom at each node, displacement and a slope w theta like this. In the right hand side we have zero matrix because we are discussing the free vibration. And to solve this vibration problem we are using this Eigen Equation concept that also already we discussed. When we form this element characteristic equation in this format, K minus omega square M multiplied with this U displacement matrix and this is the null matrix. Then to solve for this omega we are going to say that U cannot be 0 because it is a displacement matrix. The only option to satisfy this equation is this one, K minus omega square M should be equal to 0. For that we are framing this Eigen equation. Based on this Eigen equation we are evaluating this omega value which is called the Eigen value. In this example, we are going to call this as eigenvalue as the natural frequency. Now, using this element characteristic equation, we will try to find out the natural frequency of a simply supported beam. In this example, we have to find the first two natural frequencies for this beam. So, in the simply supported beam, we know that one end is hinged or pinned support and another one is the roller support. To solve this problem, we are going to use only one finite element. So let us go to the finite element model. In the finite element model, we are considering the full length of the beam. For one beam element, we are considering the full length of the beam. The length of the element will become L. When you make the finite element model, we have to apply this thumb rule. Here at left end hinged support, we are having one node 1 and the right end we have roller support, we have introduced a node 2. In between there is no change in cross section or change in material, so we are having only one element for solving this problem. When we use this one element, what are the boundary condition for this finite element model? For simply supported beam, at each node we will have 2 degrees of freedom w1 and theta 1, here w2 and theta 2. The hinged end at node 1, the displacement w1 will be equal to 0. Similarly, at roller support at node 2, we will have w2 equal to 0. So 2 degrees of freedom will be 0 here, and the remaining 2 degrees of freedom, that is theta 1 and theta 2, will be there. So these 2 degrees of freedom will give us the two natural frequencies for this simply supported beam. It is a one element model, so we can first establish the element characteristic equation. This is the element characteristic equation. This is the general format of the element characteristic equation for any beam problem. Stiffness matrix minus omega square mass matrix multiplied by displacement matrix and null matrix in the right hand side. So K matrix we are writing here the 4 by 4 matrix EI by L cube 12 6L minus 12 6L like this. So now similarly here we are writing the mass matrix rho AL by 420 156 22L 54 minus 13L like this. If you remember this K matrix and the mass matrix, then only we are able to solve this beam problem. And here we are marking these degrees of freedom, that is nodal parameter W1 theta 1 W2 theta 2. Right hand side we have 0 matrix. It is a one element model, so we can directly apply the boundary condition for this element characteristic equation to solve the problem. Let us see what are the boundary condition for this simply supported beam at node 1 W1 0. So W1 is here, this is the degree of freedom. So the corresponding rows and columns are row 1 and column 1. So we can eliminate row 1 column 1. So like this, row 1 and column 1 both in the mass matrix and stiffness matrix we can eliminate. And node 2 we have W2 0. So W2 is here. So the corresponding rows are row 3 and column 3. So we are eliminating row 3 and column 3 in both the stiffness matrix and mass matrix. So we will get the remaining 2 by 2 matrix for K and M matrix. Then we can solve this 2 by 2 matrix to get the two natural frequencies. So let us go to the solution part. This is the 2 by 2 matrix we are getting after eliminating the two rows and two columns by applying the boundary conditions. So EI by L cube, here we have 4L square, 2L square, 2L square, 4L square minus omega square rho AL by 420, here 4L square minus 3L square minus 3L square, 4L square, theta 1, theta 2, 0. Now we have to frame the Eigen equation. For that we will say, since theta 1, theta 2, these degrees of freedom cannot be 0 for a vibration, so this matrix part will be equal to 0. So for that we are going to find the determinant of this matrix. Then we are going to use this is equal to 0. By using this determinant of this matrix, we are able to find out the values of this unknown omega in terms of E, I, L, rho, A, all these terms we will get. To process this determinant, we are going to divide these two matrices by EI by L cube. So we will get this EI by L cube term in this denominator. Then we will say this total term going to be as a lambda. Then only we can easily add these two matrices. We'll see. Let us say lambda is equal to rho A L power 4 divided by 420 EI omega square. Right? This is this total term we are going to say it's a lambda. We can easily add these two matrices 4L square minus 4L square lambda. Similarly 2L square minus of minus 3L square lambda. So it will become plus 4L square minus 4L square lambda, 2L square plus 3L square lambda. Like that we are getting 2L square plus 3L square lambda, 4L square minus 4L square lambda. Now we can eliminate this L square term. So you will get 4 minus 4 lambda, 2 plus 3 lambda, 2 plus 3 lambda, 4 minus 4 lambda. Determinant of this will be equal to 0. So now we have to expand this one to find the determinant. Multiply this major diagonal term and subtract the product of this minor diagonal terms. So 4 minus 4 lambda square minus 2 plus 3 lambda whole square. So expanding this we are getting this quadratic equation in terms of lambda 7 lambda square minus 44 lambda plus 12 equal to 0. Using calculator we can solve this equation. Then we will get the two roots for this equation considering the smaller value as the lambda 1. So lambda 1 is equal to 0.286, lambda 2 is equal to 6. So this lambda 1 value going to give the first natural frequency omega 1, then lambda 2 will give the second natural frequency omega 2. Let us see. For lambda 1 value 0.286. So what is lambda? Lambda is assumed like this. rho A L power 4 divided by 420 EI into omega square. Now substitute this lambda value in this equation. We will get omega square is equal to 0.286 multiplied with 420 EI divided by rho A L power 4. Then taking the square root, we will get omega 1 is equal to 10.96 divided by L square root of EI by rho A. This is the angular frequency value. The unit for this one will be radian per second. This is in terms of radian per second. To convert into cycles per second or hertz, we have to divide by 2 pi. Omega by 2 pi will give the frequency value in terms of hertz. So Fn1 will be equal to 1.744 divided by L square root of EI by rho A in terms of hertz. Unit for this one is hertz. Similarly, when you consider the lambda 2 value is 6. Substituting the lambda 2 value in this equation, we will get omega 2 square is equal to 6 into 420 EI divided by rho A L power 4. Now taking the square root, we will get the omega 2 angular frequency 50.2 divided by L square root of EI by rho A. Now dividing this omega 2 by 2 pi, we will get the natural frequency in terms of hertz. So Fn2 is equal to 7.99 divided by L square multiply with root of EI by rho A. This is a unit with the hertz. Already we discussed how to control the frequency of vibration. This EI, product of E and I is the fluxural modulus. We can control this one, or this in the denominator we have mass. Rho AL will nothing but mass and the length of the beam. Controlling this parameter, we can easily control the natural frequency of the beam, whether we are going to increase the natural frequency of the beam or decrease the natural frequency of the beam. Based on that, we can play with these terms, geometrical parameter and material parameter we can use. Now these are the two natural frequencies we derived using only one finite element for simply supported beam. Next we will see for the fixed beam. We are considering the fixed beam problem. So for the fixed beam shown in figure, determine the natural frequency. So here this is the fixed beam given, both ends are fixed. That means in case of fixed end, all the degrees of freedoms are arrested. So you will get 0. So how to make a finite element model for this? If you want to solve this problem using only one finite element, so when we use the full length of the beam, let us say this is the length of the element L. At node 1 we will get W1 theta 1, at node 2 we will get W2 theta 2. Since it is a fixed end, both W and theta will be 0. So we are not able to solve this problem using only one element. Then what is the possible solution for this? We can use the advantage of the symmetricity. For the fixed beam, if you take the midplane, with respect to the midplane, load, geometry, material and boundary condition all are symmetrical with respect to midplane. So we can select length of the element as equal to half of the beam length L by 2. So in that case we are able to introduce a node here. At this point we can get, let us say node 2 is here, and we will get a W and theta 2 degrees of freedom. At this point, when you make this theta 2 is 0, because at the maximum deflection theta 2 value will be 0. So you will get at least a 1 degree of freedom W. So for 1 degree of freedom we are able to find a 1 natural frequency. So that is why it is given, determine the natural frequency, not natural frequencies. For fixed beam problem, if you use one finite element, we are able to achieve only one natural frequency. If you want to get more number of frequency, we have to use more number of elements. Now this is the finite element model for this fixed beam problem. Here I am showing the line diagram of the fixed beam. So both ends are fixed, and we are using the parameters like Young's modulus E, area of cross section A, and rho mass density I, moment of inertia. L is the length of the beam. For this fixed beam, to evaluate the natural frequency, we are using the concept of symmetricity. So for this beam, load, geometry, material property and boundary condition all are symmetrical with respect to the midplane of the beam. So we can use the half length of the beam as the finite element length to solve this problem. This is the finite element. Node 1 will have W1 and theta 1. Node 2 will have W2 and theta 2. Length of the element LE is equal to L by 2. Now, what are the boundary condition for this finite element? At node 1, since it is fixed end, we will have W1 0, theta 1 0. And node 2, we have W2 and theta 2 will be 0, because at the node 2 will mid span will get the maximum displacement, so slope will be 0. So this will be theta 2 will be 0. Now we have 3 degrees of freedoms are 0, so we can easily solve this problem for one natural frequency. Let us see. This is the element characteristic equation for the fixed beam problem. So this is the standard format of the element characteristic equation. Stiffness matrix K minus omega square multiplied with the mass matrix M and this displacement vector U. Right hand side we have 0 matrix. We are writing this stiffness matrix K and M matrix, mass matrix. What is the difference? The length of the element here is LE. LE is the length of the element, which is equal to L by 2. So after finding this natural frequency value, finally we are going to substitute LE value is equal to L by 2. So up to that, we are going to treat this as the element length LE. This is one element problem, so we can apply the boundary condition directly. What are the boundary condition? Let us see. For this fixed beam, node 1 we have W10, theta 10. So for W1 we have row 1 and column 1. Then theta 1 we have to consider the row 2, column 2. Then at node 2 we have theta 2 0, so we can eliminate R4, column 4. So that is for theta 2, this is the corresponding row and column we can eliminate. After eliminating 3 rows and column, we will have only one term remaining in the matrices. So using this term, we can easily establish the natural frequency omega for this fixed beam problem. So we are writing the remaining terms EI by L cube. Here LE represent the length of the element. 12 minus omega square rho A LE divided by 420. Here we have 156, omega 2 equal to 0. Since omega 2 cannot be 0, we can say determinant of this will be equal to 0. So this is our Eigen equation. Now directly we can write the equation for omega square. So we have only one term. We can write omega square is equal to 12 EA by LE cube 420 divided by 156 rho A LE. So on simplifying this, we are getting 32.308 EA divided by rho A LE power 4. Taking the square root of this value, we are getting omega is equal to 5.684 divided by LE square root of EI by rho A. So we are keeping this radical term constant for all types of beam for easy comparison purpose. Now this omega is in terms of element length LE. So we have to substitute the value of LE is equal to L by 2. Actual length is L by 2. Substituting this, where omega value will become 22.736 divided by L square actual beam length root of EI by rho A. Now divide this omega by 2 pi, we will get Fn is equal to 3.619 divided by L square root of EI by rho A. So this is the natural frequency for the fixed beam. We are getting only one natural frequency because of the boundary condition, and also we used the symmetricity concept to solve this problem. Suppose if we want to evaluate more number of natural frequency for any type of beam, we have to use more number of elements. More number of elements will give us more natural frequencies. Now in this part we have discussed how to evaluate the natural frequency of simply supported beam and fixed beam without using any numerical values for the material property and the geometrical property. In the next part, we will take up one example with numerical values for all these parameters. That will give you better understanding. Thank you. Thank you for your passion listening.